about this, but I want to make sure to share it with everyone. Let's see. No. Let's see here. So those of you guys that were in lab, the in-lab partner, we did talk about this, but I did want to mention it in lecture to everybody, including the remote partners. It was just a little bit of a brief reminder on op-amps, because I'm not sure how much you guys got to cover that. Hold on, I just want to make sure this is recording. Yeah, it is. Okay. Since last semester, since most labs are remote, I don't know how much you guys got to use op-amps and the like, but we did find an error with the use of the 741 op-amps in some of the group circuits. And that I wanted to explain these diagrams for op-amps. And we're just going to go pin by pin a little bit. That the first ones on either corner here are offset null, and these are for fine tuning your op-amp for any slight DC offsets that are going to be produced within the transistors within the op-amp itself as well. You have your inputs, one being non-inverting and one being inverting. And I think most of you guys put your signal in this way, and this guy was connected to ground for some of the circuits, but doesn't necessarily have to be connected to ground. I'm guessing in your circuit diagrams, for those of you that did, the ground is providing your relative reference for your input signal, but also for your power supply to the op-amp as well. And this is where some of the error came in, or issues came in, that the 741 op-amp is a dual power supplied op-amp, which means you have to provide a positive voltage and a negative voltage for it to actually to work correctly and to have the adequate power. There are op-amps where you only need to provide power into one pin, but this one specifically requires dual supply. So if some groups were using these without, with only one voltage supply being provided, which meant then the transistors weren't being powered, you weren't having a current differential across the transistors within the op-amp that actually make the gain happen. So that's what I wanted to point out. And then this NC means no connection. This doesn't do anything over here. And then you read the output from there. So I did want to note that it's a dual power supply for the 741 and the OP42 that you were using. And that's how to understand like what these different terms or pins mean. I also included, if you guys weren't aware, on the course YouTube page, I do have a playlist that says videos relevant to Phys 204, 208. That includes a lot of the videos I link in the notes, but it also includes some videos like Professor Rule has a couple of videos explaining like the raw board, grounding, but also some other helpful videos that I've just added 3 videos going over some background on op-amps if you want to look in more detail with that. Because this is some details of circuitry that's not really in the syllabus for this course, but just to be aware. Okay, in the chat. Yeah. And 3 Blue, 1 Brown is a great series of videos. I don't think he gets into the electronics, but definitely some of the concepts and math behind what we're doing. Yeah. So that's a great way to complement how I explain things. People have on YouTube are explaining it in other ways, and it's great to hear those different opinions. So any questions with the op-amps? Okay. So today we're going to get into signal averaging, how to change your data and improve your signal to noise ratios using software methods. You spent all of last lab doing hardware methods with your filters. Also understanding how frequent you should be sampling your data, and the fact that we're working with discrete and finite data, that issues of sampling have already come up in lab for some of your groups. And then we're going to briefly touch on correlation analysis, which is another mathematical concept of signal processing that's going to be different than what we've discussed previously with convolution or Fourier transforms, but another important mathematical way to process your data. So like I mentioned, this will all be in lab 4. It's going to be a longer lecture today, so you get this content, and then next week we'll briefly review this content. So goals for today, defining what signal to noise ratio is in a more quantitative way than what we were using in lab 3, specifically for a DC signal. We're going to talk about the software methods after you collect your data. How can you improve the signal to noise ratio, and how we can quantify that improvement specifically with signal averaging. We're going to discuss multiple software methods, but the main one that you'll be using is signal averaging, and is one of the more commonly used ones. So that's all on signal to noise ratio and improving that. Then we'll be talking about how often should you be collecting your data and sampling. So with sampling, what's the minimum frequency that you have to collect your data and still reproduce your signal, which is the Nyquist frequency. We'll define that. We're going to show that qualitatively with some diagrams or some plots, but then get into some quantitative assessment of if you're below or above, what will your signal look like? And then I mentioned we'll touch on correlation. But all of these about, you can see in these goals, quantitative. We're going to get in a little more detail of how to quantify those improvements or what you're observing with your samples. That in the first 3 labs, we were a little more hand wavy on, or doing visual qualitative inspection instead. Okay. Let me get my notes organized first. Okay. So we're just going to start out by defining signal to noise ratio and signal and noise. So we were talking about signal to noise ratio in the last lab. Do any of you guys have a definition that you would provide for what a signal is? In the broadest sense, I guess.
I think in the lab we went with like the amplitude of the signal divided by the amplitude of the noise, taking like the amplitude of the noise to be what, 2/3 of its peak to peak.
Yeah, so I'm even more simple right now. What would you define a signal as when you're collecting data? So even more simple than that, I'm just saying the signal when you guys were working with those square waves, that was the square wave that you were feeding into your summing circuit. That's what you wanted to detect. So that's what we're going to define as a signal, is like the output of your measurement that you want to observe. Versus a noise is unwanted signal, things that you don't want to detect, something that you want to remove. And this ability of that you want to remove this, some quantitative factors of the noise make it so you're able to remove the noise. So you guys have been working with white noise so far, and we can say that in many typical measurements that the average magnitude of the noise is constant. It's typically constant and isn't always, and we're going to go in detail 2 lectures from now about different types of noise. So the fact that it's typically constant and also that it's independent of the signal. Makes it so that there's ways that we can creatively remove the noise from the signal. It's also worth noting that Noise is always going to be present. You can't completely remove it. And I'm underlining always, I'm saying it's always present because when we get into details about different sources of noises, there's noise that arises from quantum effects and thermal effects, and there's no way that we can remove quantum mechanics from our measurements or perform a measurement at absolute 0 Kelvin. So because of that, it's always going to be there, but there's ways that you can decrease the effects as well. So then Jack was getting into more of the quantitative definition of signal to noise ratio. So I'm just going to write that as S/N. And this is a figure of merit to quantify the effects of noise and signal against each other. And it kind of captures that as noise increases or signal decreases, the effect is greater. Just by simply taking that ratio. So yeah, Jack was defining how we describe signal to noise ratio in lab 3. But here for a DC signal, we're going to get a little more quantitative. We're going to say the signal to noise ratio is going to be equal to the average of that signal divided by the standard deviation of that signal. So this is also the same as the inverse of your relative standard deviation. If you've taken some statistics courses, if you've worked with normal distributions, Gaussian distributions, the relative standard deviation is going to be that standard deviation divided by the average. So it's flipped here. So we're going to say X bar is going to be the average of the signal. Sigma X is the root mean square of the signal. And RSD, that's relative standard deviation. There. So this is how we're going to define it. So any questions with just this brief introduction to signal to noise ratio? Okay. So now getting into reducing the effect of noise, improving our signal to noise ratios. And one way you can do this is hardware, which I already mentioned is what lab 3 was about, that you can use electronic components to remove different frequency ranges of the noise. So you did that with your low pass filter, your high pass filter, your band pass filter. You can also, there's other hardware methods of shielding noise. So if you have some type of environmental noise that would interfere with your measurements, you can have some grounding. Faraday cages, we'll talk about that when we get into a lecture that's all devoted to noise. So that will also be in the future. Today, we're going to be focusing on software methods. So after your data is collected, so this is something that you can do in Origin, MATLAB. You'll be doing some of that with your data once it's read. Also, some of the instruments do the software approaches themselves. With like their onboard computational capabilities. I think think Robert and Lucas were playing around with the DSO, that it has signal averaging capabilities. In lab 4, you'll do that where the computer within the DSO itself can do averaging and one of these software approaches. So signal averaging is the first one we're going to talk about. Which you'll also hear it referred to as ensemble averaging, or also co-addition, are all different terms from that. And it's really, you're averaging your signal. So you collect successive sets of data. You're going to sum those point by point. Typically on the x-axis with your dependent variable. So with our data, it's in the time domain, typically. And then you divide, since it's taking the average, divide by the number of sets that you collected. So what this would look like is if we have some type of signal here versus time, you might collect one data set. Let's say we're expecting to see something that's somewhat Gaussian. It could be one set of data. Let me change my pen color. You might have another set. And I'll draw one other set here. Let's do this green. That your data here all lines up in the time domain. So then I'll switch to black here. That in each of these time bins, each of these data points, you're going to take this data, the spread here, you're going to sum those together, divide by 3, and plot the average. So that's why I'm drawing in black here. And the notes I've uploaded online, you can see I'll include a legend there. So your output would then have just these X data points. That should smooth it out, which obviously here is a little hard to represent since I'm just drawing this freehand. So at each of these, sum 3 data points. From each set and divide by 3. And I'd also like to emphasize this is something that people will forget or get confused about, that they forget this dividing by 3 aspect. That, let's say for a Gaussian function, let's say that you take some noisy signal here. It has some width sigma. It has some amplitude A here. That when you take the ensemble average, you should not expect your data should be smoothed out. But sigma and A for these data sets should remain the same. Your amplitude does not change. Your sigma does not change. Also, you have some center value here, X naught. That does not change. that you might have higher accuracy, you might have higher precision. So accuracy, you might be more confident in where X naught actually is, or what the amplitude actually is, and what sigma actually is. If you compare multiple data sets that you've averaged together, you should have more reproducible results with that average of precision. But the properties of this function here should not change by taking signal averaging, like just the certainty. I've seen the data looks, it does look smoother when you do ensemble averaging, but I will note that that's different. When you're talking about signal processing, smoothing data is actually going to be like a mathematical modification of your signal. So it is different. But it might seem redundant here that I'm saying A, sigma, and X naught do not change. But I've graded many lab reports where people say, oh, after ensemble averaging, like the Gaussian becomes narrower, the amplitude becomes higher. That's not what's changing. You're having higher accuracy in what those properties for your signal are. So I did want to emphasize that. And so that's kind of a qualitative discussion of signal averaging. I also want to get into, when you perform signal averaging, how much better will your signal to noise ratio be? What can you expect? What type of improvement would you expect to see in your signal to noise ratio? What can you expect to see improve? For lowercase n sets of data. So we're going to do a quick derivation here for this, that we're going to say our signal is capital S for a given signal S. And then we're going to say we're going to take n repetitive measurements. So those are our variables there. We're going to define our mean signal as S sub x. That's going to be equivalent to, we're just going to write the average here. The summation of 1 I equals 1 to n number of sets, all divided by n here. And then our noise is going to be the deviation from, at a given set, is going to be equivalent to the difference in our signal of that set, S sub I, minus the average here. That's how we're defining noise. So we can then, as we said, like root mean square is going to be how we're defining our noise and the signal to noise ratio. So we're going to then take this definition of noise here to the variance of our signal. And that's equivalent to the mean square of the noise. So we're going to take the summation, this difference. Here's the mean. This portion is the mean, and then this is the square. So this is a variance our signal. Then we're going to say our noise level for our signal to noise ratio is the root mean square, which would then be the square root of this. So we're going to say for a given data set, our noise and our signal to noise ratio is going to be the root mean square, which is the square root of the variance. So there we've defined our mean signal and our root mean square for our noise here. So then if we take n repetitive measurements, our total signal for all of that, S sub n here, is going to be the sum of all of those individual measurements. And looking at how we define our mean signal, this would then be equivalent to n times our average signal here. In contrast, for n measurements, if we want to get the total variance, this would then be the total variance. So I'm going to be the sum of all the variances. Which then is equivalent to n times our average variance. This should be, over here, this should be the x. Over here, I think. So then if we want the root mean square, we then take the square root of this. So for n measurements, would then be the square root of n and the square root of our average variance here. Which then would be equivalent to the square root of n, or the number of measurements we've taken, times our noise. So then we have for n measurements our signal, our value for our noise. So then the improvement for n replicate measurements, we can then take this ratio, n times our average signal, square root of n times our average noise. And then the improvement for n replicate measurements is going to be the square root of n times the signal to noise ratio for one measurement here. So this is the big takeaway with this derivation. I know there's lots of n's that I was saying, problems with replicate measurements and noise. But the signal to noise ratio improvement, I'm going to write this out because it is a very important point. Is going to be proportional to the square root of the number of data sets collected. That you collected, and then you do the signal averaging. Starring that, so that's a big takeaway of why you perform signal averaging, that you can prove it by a factor of the square root of the number of measurements that you take and average together. So any questions about signal averaging right now, qualitatively or quantitatively? Okay, so I want to briefly mention a couple of other averaging techniques that you may run into and also it's not always possible to do signal averaging. That another method that you may see is boxcar averaging. And this means that you're averaging, instead of multiple data sets within a single data set, you can average over the time domain. So let's say we have some signal that's changing slowly over time is a key thing here that hopefully you'll see that if we wanted to do boxcar averaging, over a data set of 3, what would you would do is in these boxes here that I'm drawing, you would be averaging 3 data points at a time, and so on and so forth. So then you would take the average of these values, and that would be your new data point. So you would box a group of data points along the time domain or the x-axis, average them together, and produce a new data point. So here in this example, some drawbacks to the boxcar averaging technique is that you lose resolution in the time domain. So here we're losing by a factor of 3 here. But a benefit is that you do not require replicate data sets. So with signal averaging, you have to have the ability to collect a data set, repeat it. That's been pretty easy in the data that we're working with in the electronics lab, where you're looking at periodic signals. There's no limitation there. But if you're doing like an experimental lab with limited amounts of reagents, with a time-dependent process, maybe you aren't able to collect data over and over and over again. Maybe you have one shot to collect your data. It might be very easy to collect a high frequency of data relative to that change. So in that case, boxcar averaging might be a better choice compared to signal averaging. If you only have one set of that data, you can't repeat the data. But again, because you lose resolution and because you're averaging over the time, you have to also know the frequency over which that you're averaging that data versus the frequency that you expect your signal to change. So you must, I guess I'm talking about frequency in the time domain, you must assume the signal changes slowly. I guess no. Is better than assume. So it changes slowly in time compared to the noise and your averaging window. A way that you can overcome, let me change the pen color here, the loss in the resolution of the time domain. You can overcome this by modifying this slightly and do a moving window average. So instead you can, doing every 3 data points here, you can still average 3 data points, but only shift your box over by 1. So you get the same, you maintain a very similar time resolution here. So it's very similar to the boxcar method, but it moves 1 data point at a time. And the last one I want to mention, change back to, just using different colors here to indicate this. Is polynomial smoothing. Sometimes you also hear it referred to polynomial filtering, but this is a more complex averaging techniques where you weight the data by convolving with a polynomial. So this is equivalent to taking a subsection of your data and then doing a curve fit to a polynomial and taking the center point of that fit. So this is a little different than taking the average that we've been talking about, signal averaging, boxcar averaging, moving window averaging, that this is a nonlinear method. And the reason I mentioned it in this class is that polynomial smoothing comes up in, you can do it in Origin. If you're working in Photoshop and you're doing smoothing of an image in 2 dimensions, there's polynomial smoothing filters there. And it's important to know that this can distort your signal if you're not aware of what it's doing. So just be aware that it can cause some issues. And it's also referred to as a Savaditsky-Golay filter. You'll also see that show up probably in some built-in functions. And that's named after like the 1964 paper that introduced this method. And in the notes, I've linked it to this paper. It's in analytical chemistry, actually. And it's been cited over, last year was over 14,000 times. But just if you want to see, it was introduced in a chemistry journal and then it's been applied to all these different applications. So we won't be using this smoothing, but like I mentioned, you should be aware that it can have issues depending on how much of the data it's fitting, how much it can skew that data, and the like. So let me see. Yeah. Any questions with these alternative software techniques for improving your signal to noise ratio?
So where it says you're just convolving data with a polynomial, I'm sure there's a way to choose a polynomial, or can you just, like, what does that do?
Yeah, so I should have included like the animation that I think is in the notes, but the polynomial, I think in a lot of the built-in ones, it'll be, the polynomial will change the number of terms within that polynomial. And so it'll start with like the full set of data, then reduce it down. And you'll have like this, just like with convolution, where you guys were seeing your data shift past one another, the polynomial is going to shift and change based on how much data that you're approximating or how much data you're trying to smooth out. So I guess the convolution concept is like, yeah, multiplying those your data versus this polynomial, but at each step that polynomial can change. So that's where like the curve fitting aspect that I mentioned here is. So we don't need to get into like the details of behind that. And I think I also linked to another YouTube video, but I just wanted to let you guys know that this is a method that you'll see built into stuff, and you should understand like a little bit behind what goes behind the scenes there. So I don't know if that answers your question, since I'm not getting into the specifics of how it works, but if you're interested, we could talk about that like in office hours or something. Okay. Any other questions? Okay. So moving on, yeah, last little bit about these different signal to noise ratio improvement methods is that, like I was emphasizing with the polynomial smoothing, that there's drawbacks. With the boxcar averaging, there's drawbacks. And we've talked about these a little bit, that with signal averaging, you have to weigh and you'll see this in lab when you guys work through it, is that sure, it's very nice to get the square root of n improvement, but how much time does it take to collect n extra sets of data? That sure, maybe you'd want to improve this by a factor of 100 or so, or 1,000, but do you have time to sit and wait for 10 to the fourth extra collections of your data? Or if you're trying to look at a time dependent process, like I was talking a little bit about, if you have limited reagents, that if you're trying to look at a non-equilibrium process or time dependent signal, can you actually collect that extra data? I guess I was giving an example of something I would think in my own lab. If you're doing something with biophysics, you're trying to mix a protein and a ligand together, an enzyme and a ligand, and after you mix them together, then everything's produced to the product. It's not very easy to take that measurement, look at it again, look at it again, look at it again, unless you're taking and mixing those together every single time. So that's going to use reagents. Or you can think of like an astronomical observation, like you only have a little bit of time where that star is in the sky or something, and then you'll have to wait till the next night to collect that data and collect that data again. That you might not, it might be really challenging to collect these extra n sets of data, limited by what you're doing. And like I mentioned, non-equilibrium processes, you're going to have to synchronize your data as well, the data collection. So this is where you guys should be quite glad that you're looking at these periodic signals. So it's very easy to synchronize these things as opposed to something that might be a burst. With boxcar averaging, we discussed that you're going to decrease your data sampling. With your, I guess, your output of the filter there, or the output of your average. So it's going to be decreased by a factor of 1 over p, where p is like the number of points you're averaging over. So this is your average frequency versus your original frequency. So that's the drawback of boxcar averaging. And this average frequency then can lead to, like, you need to know how many samples you need for a given signal. To then know if your boxcar average is going to cause you issues or not. And this is what we're going to describe next. So we're going to get into sampling on the next slide, but I just want to check in right here. Any other questions about signal to noise ratios, averaging techniques at all? Okay. So this is the other topic, I guess the second topic that we're going to get into, in a little more detail is sampling. So, and this is what you've been doing throughout the semester so far. Like in the first lab, you guys were asked the question of how many samples does the KDMM reader collect? And you have to think about that sampling rate of, you can only collect 7 samples per second or so. I guess most of you guys define between like 6 and 10 points per second. How does that frequency that you can observe your data, how does that then change what you see in MATLAB versus what the continuous sample that you're producing on your ARB, what's going on there? So sampling, we're going to define as the reduction of a continuous signal to discrete observations. And this is the equivalent of kind of taking your continuous signal, your discrete observations here is pretty much the equivalent of multiplying your continuous signal with a Dirac comb. So if you remember, our Dirac comb signal looks something like this. And that's going to be our sampling, our sampler. So we're going to take the sampler, this Dirac comb, and it's going to have a set frequency that we're going to say is f sub s, so the sampling frequency. So it's the equivalent of taking this and multiplying it by your continuous signal. So we can sketch this out for some given signal. This is our continuous signal. We're then multiplying it by a Dirac comb that has a magnitude of 1 here. This is also in the time domain. Those should be evenly spaced. I didn't draw them that well. Where the frequency of that is, the period of this Dirac comb is 1 over our sampling frequency here. And then when you multiply these two together, what you end up getting, I try to re-sketch that guy out here. It's 1 times that value. These are our Dirac combs multiplied by that signal. You get your discrete data points out. The big question with sampling is what frequency, what sampling frequency here do we need to accurately get out our continuous signal? Where our waveform is our continuous signal. And this is where the answer to this question is defined by the Nyquist sampling theorem, which is the other important takeaway from today's lecture. Where this answer is that your sampling has to be at a frequency that's twice the highest frequency of the components making up your signal. So I'm just going to write this out, and then we're going to explain this both visually and mathematically as well. Here. So the key things here is at least twice. So there's going to be a 2 in the equation. And then this highest frequency of the components making up the signal is a separate frequency called the Nyquist frequency. So we have here our f of s, our sampling frequency. That's what this sampling is, twice the highest signal. So we're going to define this. Our sampling frequency, f of s, has to be twice times f of n, where f of n is our Nyquist frequency. And that's going to be, in this definition here, the highest frequency component of the signal. So this is the text definition. This is it written out in the text. And I do want to know, or I do want to let you know that depending on the field and depending on the book, you're going to see different definitions of what f sub s is, f sub n is, Nyquist, sampling frequency. So it's not very standardized in the field of, here we're talking about in physics, you'll see it in analytical chemistry, you're going to see it in information technology, you're going to see it in communications. So depending on that field, there's different definitions that you'll see. So be aware that this is how we're defining sampling frequency and Nyquist frequency. And when the quiz asks you about what the Nyquist frequency is for a sample, like this is the definition, these are the definitions that we'll be using. So just study, just know that those are the terms are, but if you're in a different class, if you move on to electrical engineering later down the line or communications, you might see slightly different definitions there. And I'm mentioning like information theory or communications because that's really where this theorem got defined and the people in the history. You'll also see, so Harry Nyquist, who defined this theorem, worked for Bell Labs and defined this in the 1920s about sampling needed for telegraph communications. And then you also see this referred to as the Nyquist-Shannon theorem as well. And that's, the Shannon is for Claude Shannon, who developed this theorem simultaneously for like telecommunications as well. And also was derived by several other people in electrical engineering, in mathematics, and they all independently came up with this theorem for very different applications. But that shows you the importance of sampling, that it is relevant to many different fields. Now I have no idea how my notes are organized. Okay. And also to note that this frequency, also you'll see it referred to as the folding frequency. And in one of the examples that I'll show, that why it's called folding frequency, that if you're sampling less than 2 times the Nyquist frequency, you'll see the signal fold in upon itself. And we'll visually show this in one of the YouTube videos I link as well, shows what we mean by folding, that it will start to overlap. And I'll show that in a couple slides later from here. So to sketch this out and what the importance of the Nyquist sampling theorem is, we'll see how good my sampling skills are. So I'm going to draw just a simple sine wave here. Where this is going to be our period, capital T. And with the definition that we defined here, that's going to be, so this is going to be our period here. That's going to define our highest frequency component, 1 over the period here. So the definition that we wrote out, the Nyquist frequency has to be twice that frequency or half the period. That's going to be our Nyquist period here. 1, 2, 3, 4. I'm going to sketch this out to have one more. Okay. So with that signal, we can then draw from this different sampling. So this is our underlying true signal. So the purple right here is our true signal, our continuous signal. And then for our sampling, that Dirac comb that we're going to multiply by here, we're going to do different amounts of sampling here. So the first thing I'm going to do is I'm going to sample at 3/4 of our Nyquist period here. So this is going to be the red X's I'm going to draw here. So we're going to start at our 0 point here. 3/4 will then take us over here. Here. This peak. And obviously I didn't draw this very even. Okay. So if we take this 3/4, I'm going to sketch this below. The resulting data points look something like this. And if this was your output and you knew it was a sine wave, what you would be prone to do is sketching out a sine wave that looks like this, where this means that we undersampled our signal. And what undersampling does means it misrepresents the true signal. As a lower frequency. So if you're ever sampling less than 2 times your Nyquist frequency, you're always going to get an output of a lower frequency signal. And there's a term for this, and this is called aliasing. And this happens when the Nyquist criterion is not met. And then you get undersampling. You'll also hear inadequate sampling, and the reconstructed data is misrepresented. So that's an example of undersampling. we can then take the same data, I'm going to use orange here, and I'm going to do this exactly at the Nyquist frequency, or 2 FN. So if I do that, we're going to start exactly at 0 here, and we're going to get a very special case that if we do that, and your signal starts exactly at 0, your sampling starts exactly at 0. This is kind of a special case where then we end up just having like this flat line or so. So this is an example just for a sine wave, that this is a special case of aliasing. And I'm showing this special case, so this would be like kind of a violation. Well, yeah, violation of the Nyquist sampling theorem, because right at 2FN, we should be able to reproduce the signal. And if we shift this slightly over, let's say if I draw these boxes, we would actually be able to recover the signal, that we would get that frequency component. That if I draw this out, we would recover our underlying signal, that we would be able to sketch that out. So, but I'm showing this special case to kind of emphasize that while the Nyquist sampling theorem says that we should be fine if we're 2FN, it's actually better if you're slightly above 2FN. It's better to be on the safe side. I guess a rule of thumb is, and you might actually see in the literature or in textbooks that they'll say like 2FN is the minimum, but it's better to sample at 10 FN, or depending on the field, they'll say that. Or you'll also see in books where they'll say greater than 2 times the Nyquist frequency, greater than or equal to, or so. So that's why I was emphasizing that special case, that if you have the ability to sample faster, it's better to do so. And when you guys work through the lab, you'll see that as you change your sampling. And then for this last one, I'm going to do like, okay, let's do it at 9 F of N, somewhere that the textbooks say is much better. And if we did that, what we would end up seeing is, I guess I'll draw some triangles. And I'm not going to sketch all of that out in the interest of time, but you can clearly see that if we're much higher than the Nyquist frequency, it's very easy to recover what our true signal is, and no risk of aliasing. So we very nicely get the signal shape out over here. So that was my bad sketching skills, trying to show you guys the sampling theorem. But it emphasizes that you should have a good idea of how frequent you should be sampling your signal. You should have an idea of what frequency range you're in. And to further emphasize this, here's a sketch that I'm not going to do by hand. Here we knew what the true continuous signal was. But let's say you have some output here of some data that looks like this. And you have some discrete data points. That's what all the signal versus time here. And if this was your output, a question would be, is this what your signal is? Is it this frequency of sine wave? Or would this be adequate as well? So with the red and with the orange, a question is, out of these two fits that I've provided, which one fits the data? And the answer is both of these fit the data. Where this case would be, you would have aliasing, and this would be okay. That you need to have an approximate range of what frequency your underlying data is, or you might run into this situation, which is not too good. Or if you know that you have a lower frequency signal, then you can have some confidence that your sampling is okay. So you don't want to run into this case where you accidentally have aliasing taking place. So in the case of aliasing, we can further quantify this of what type of alias signal or what type of frequency you would expect out if you do have aliasing present. So we can quantitatively describe this. So and this is going to be based on, so we're going to call this our observed frequency here. And this is going to be related to the frequency of your signal. So this is the observed frequency, frequency of your signal. And we're going to say this signal is a sine wave. And what it's going to appear as is some multiple, integer multiple of the Nyquist frequency. So we can also say this is equivalent to your observed frequency plus or minus some integer multiple times G, where G here is going to be some frequency below 2 times that Nyquist frequency. So again, looking at this, if G is greater than 2 times the Nyquist frequency, you'll get the correct signal out. But if it's less than that, you're going to have an alias signal, an undersampled signal here. So some important things to note is that you have this plus or minus that value here. So in lab 4, you're going to be working with simulated data and looking at the simulated, looking at the aliasing based on the sampling that you're doing. And you'll build up a table of your observed frequency versus the true frequency. And you should see this trend of plus or minus on other side of some integer multiples of that Nyquist frequency here. So when you get to that part in the lab, you should refer back to this equation here that we can quantitatively describe what the aliasing is present. Okay. So any questions so far with sampling and Nyquist frequency?
Okay, maybe you already said this, but in case you didn't, what is the n supposed to be? I mean, I know it's supposed to be an integer multiple, but
yeah, it's going to be an integer multiple like that.
Oh, that's it.
So
Okay,
like,
just some integer multiple.
Sorry?
Does it represent something physical? I don't know.
So that will be related to, so it's going to be related to your sampling. That's a good point. It's going to be related to your sampling frequency there.
Okay.
Any other questions? Okay. So a little bit more about the sampling theorem, and this is where I'm going to explain like why it's called folding, also called the folding frequency. And we're also going to work in like Fourier transform and the convolution theorem. So we're going to get a little bit of everything from the past couple of weeks or so that I want to show you in the frequency domain what the Nyquist sampling theorem represents. So we're going to start, let me change the pen color. We're going to say for a given signal in the time domain, we're going to say some function, capital F of t. We're going to say its Fourier transform is going to be phi of omega. And we're going to say for the signal, we're going to say it's, actually, sorry. For our signal in the frequency domain, we're going to say it's symmetric around the origin. And we're going to say that it's within some given bounds of frequency. We're going to say it's going to fall between negative omega n and omega n, where this capital N is going to be related, you can guess, to the Nyquist frequency there. So to sketch this out, we're going to say we have some given function in time, be whatever we want. So I'll just like sketch some arbitrary function, blah, blah, blah. And when we take the Fourier transform of that, we're going to get our frequency domain signal. Where for this definition that we have here, I'm just going to draw this type of shape where it's symmetric around the origin and all of it falls between negative omega n and positive omega n here. We described earlier that sampling is the equivalent of multiplying our time domain signal with the Dirac comb. So I'll sketch that guy out. And we're going to say our Dirac comb here in the time domain has a given period lowercase a. And we're sampling this at the Nyquist frequency. We're sampling based on the Nyquist frequency of the period divided by 2 here. Where this 2 is coming from our Nyquist theorem that we mentioned. So this is all in the time domain that we're multiplying, but that would be the equivalent to if we take the Fourier transform of this Dirac comb. If you take a Fourier transform of a Dirac comb, you get another Dirac comb where the period is 1 over the period in the time domain here. Remember that inverse relationship between time and frequency. So we're going to space these guys out more. And the period here, since they're inversely related, and we're saying we're sampling at the Nyquist criterion, it's going to be 2 over the Nyquist period divided by 2. So that's what our Dirac comb looks like in the frequency domain. If we said that in the time domain, it's multiplying our function in time versus our Dirac comb in time. With the convolution theorem, we know that multiplication and convolution are related. So this would be the equivalent of taking the convolution of our signal and frequency and the Dirac comb in frequency here. So this is kind of sketching it out. Hopefully you followed those Fourier transforms, the multiplication periods and stuff like that. So this is how we're visually explaining it here. So we can say that f of t multiplied by our Dirac comb, period A, is equivalent to taking our signal and frequency and convolving it with the Dirac comb and frequency. So taking this definition here, we're going to write this out, this multiplication and the Fourier transform here. So let's take this, the multiplication of these guys, and take the Fourier transform. Yeah. Hold on, I'm just checking something. Let's write the Fourier transform of the time domain. Right, the Fourier transform here is what I'm missing. So now I'm going to take this with Fourier's theorem as well. So over here, we have the Fourier transform, which is equivalent of the frequency domain convolution. So we're going to take this equation here, and we're going to remember that we can write the Dirac comb as a sum of delta functions. That are equally spaced based on this frequency component A here. So we'll rewrite this left-hand side here with the delta function notation. Where we're summing this from negative infinity to infinity, since it's a continuous signal here. That's what we're saying. And with this summation, we can take that out and move it to the front with this delta function here, since that's just, or just the summation itself. Move that out front. So we can just deal with the delta functions. And then now we can focus on this term here of just the delta function, that it's going to be 0 at all values that are not NA. And that can give us, I'm going to move this over here, that then we can just have the summation we only care about the values of our function in the time domain where it's equal to NA times our exponent. Also within the exponential term, we can plug NA in for time. That's going to be equivalent to some pseudo frequency function that then we're interested in. So we can say that's the equivalent of the left-hand side of this function. And we're going to say it's phi prime omega. So with this definition, we can then say that this also has to be equivalent to the right-hand side of our equation. And I did a horrible job of spacing this out. So if we look at all of this over here, after we do the math here, we can see that as long as our frequency function is within these limits that are related to NA, there's going to be a unique solution here. So yeah, just trying to sketch this out. That what this means is, let me insert a new slide. Ran out of space, underestimated greatly. So based on that, the sampling theorem, that's where this 2 is coming from. There's going to be a unique solution in the frequency domain based on this guy here. To this equation. That if we then take this frequency function and convolve it with our Dirac comb, it'll make sense and our output will be unique. But so this is our okay case. The not okay case is based on that Nyquist frequency. But let's say it extends outside of there. When we do the convolution with our Dirac comb, this is where we're going to have our signal fold in upon itself, that then we'll have areas start to overlap. These overlap areas mean there's not a unique solution. What you're going to get is some summation here. And these bumps that we're seeing in after the convolution, this is going to mean that there's overlap between our frequency function and the Dirac comb. So those overlaps are summed, resulting in our aliasing and resulting in the artificial seeing of something that's a lower frequency. So this part here where these things start to overlap, causing these bumps, is what is called folding. And thinking about this in terms of the frequency domain and what happens when you undersample in the frequency domain is why you'll hear the terms folding frequency as well. So you'll see that more often when people are thinking in the frequency space. So that's another explanation of aliasing and undersampling. And yeah, I think I'm going to stop there. Instead of talking about correlation, we'll pick up on that next week. And I'll just point you to the Nyquist sampling theorem is described in that digital signal processing guide. And these are some helpful explanations of sampling, aliasing, Nyquist theorem, because I do think visuals help with understanding what that means. So are there any questions at all with the sampling? I know I went through this part quickly.
Well, okay. remember when I asked about N and you said it's related to something and you wrote down FS? Is FS sampling or signal frequency?
Yeah, here, this would be the sampling frequency.
Okay, cool.
Yeah.
Thank you.
And I mean, that's the problem of in this lecture that we're talking about signal to noise ratio and then sampling as well, that lots of S's, lots of N's. So I apologize for that. So that's why I would really think about sampling, try to divide up this lecture, the notes with, okay, I'm just going to focus on the sampling, just focus on the signal to noise ratios. They are related with how you collect your data. So that's why they're in the same lecture, in the same lab. But yeah, it does lead to some confusion with those. Any other questions? Okay. And I do want to emphasize this point at the end as well, that I do want to express my appreciation for you guys making this lab work. I know it's not easy doing remote and in-person and hybrid and stuff like this, that I do really appreciate how much time you guys have been putting into this and being collaborative and patient with things. And I hope you enjoy your spring break tomorrow, and I'll see you guys next Monday then. Okay.
Thank you.
See you guys.